Hello there guys, welcome to this video where we're going to be taking a look at open and closed sets. So let's get right into it. Okay, so to start off with, let's define what a set actually is. And now I'm going to be giving you guys the non-mathematical definition first. So it's simply just a collection of objects. So a set is simply put a collection of objects. And now you guys are probably wondering, well, if it's a collection of objects, can it be a collection of animals like this? Or maybe can it be a collection of numbers like this? Now, mathematically speaking, in this video, we're going to be taking a look at sets in specifically two different kind of realms or spaces. Sets in the real number line space. Okay, so that's one type of sets we're going to be taking a look at. And other sets we're going to be looking at is higher dimensional sets. So we're going to be taking a look at the 2D space, R2, and also the 3D space. And higher spaces work pretty much the same way. So we know that a set can either be open or it can be closed. Okay. So now let me give the non-mathematical definitions of those two things right there. So an open set is simply put a set without a boundary. And you guys probably guessed it, a closed set is a set with a boundary. So some examples in the one-dimensional real number space would be, well, I can have the set 1 is less than x, which is less than 3. Okay, so it's a set of values of x that are between 1 and 3. And now notice that it's not inclusive of the 1 and the 3, or aka it's a set without the boundaries. So this is known as an open set. Now let me look at another set where we have 1 less than or equal to x, less than or equal to 3. Now notice how we're actually including the boundaries here. And this is known as a closed set. Okay, so this is known as a closed set. And open sets are written like this with curly brackets like this. And closed sets are written like this with square brackets like this. So simple, okay? So in the one-dimensional number space, it's really, really simple. You know, it's a set without a boundary and a set with a boundary. So now let's take a look at the two-dimensional space. Okay, so I've kind of drawn a dotted rectangle here. You'll understand why it's dotted in a second. But let's say this is our two-dimensional rectangle space here. So now, if I was to draw a closed set, if I was to kind of section out this box here to form a closed set, I could do something like this, okay, where the boundary is included. Let's call this set A, okay, so this boundary is included, so this is a closed set. So this is known as a closed set. Now, I can draw another set with dotted lines like this, and this, I'm going to call this B. And this is an open set because the boundary is not included. And as you can see, the rectangle outside, the whole kind of space that it's included in, is itself open because it's dotted. The boundary is not included. So it's an open set in R2, okay, in the two-dimensional space. Now let's try to understand what this means. Okay, so this is an open set right here. Now, what makes this open? Okay, what makes this open? With our non-mathematical definition, it doesn't have a boundary. The boundary is not included, so this is an open set. Now, that's not very mathematical, and mathematicians have a really, really clever way of saying why this is an open set, of defining it. And what they did is, if I pick any point, let's say I pick this point, okay, in this open set, I will be able to draw a circle around this point with whatever radius I want. Let's say we say it has radius epsilon, such that the whole kind of circle of points here stays in this set. So you can see that this whole circle of points is within this light blue set right here. And now this should be true for every single point in this set. So if I was to go as close as I can, okay, as close as I can to the boundary like here, I should still be able to draw a circle like this. And remember that I can choose the radius. I can choose what epsilon is. But the point is, I should be able to draw a circle centered at my point with a radius of my choice, such that the whole kind of region is in that set, like this. And I can go as close as I can to the boundary. Okay, and I will still be able to draw a circle, because I can just make the radius smaller and smaller, right, as I get closer and closer to this boundary. And this should be possible anywhere on the boundary, you know. So what makes this an open set are a few things, okay? So for all points, okay, so for any point in that set, I should be able to draw a circle. So a circle, center is the point, okay? The radius is my choice. Let's say I choose it to be epsilon, okay? So when I draw a circle that's centered at the point with radius epsilon, should also be in this set, okay? So this is what makes an open set open. Now, why does this fail for a closed set? Okay, why does it fail for a set like this? Well, very simple. If I pick a point on the boundary like this, okay, if I pick a point on the boundary, I can't draw a circle such that all of the circle is inside the set, because the boundary is included now, right? So I can just choose a point on the boundary such that I can never draw a circle. No matter how small I get, I can never draw a circle that's always inside this set. So that's why this fails for a closed set. So now, how do we define a closed set? Okay. Well, you see, we mathematicians are very, very lazy people. We didn't really want to go into that extra trouble of defining a closed set. So we came up with a clever way to kind of avoid that problem of defining it. So we said a set is closed if the complement of that set is open. Okay, so a set is closed if the complement is open. Well, what is the complement of a set? So if we take this set here, the complement of that set is pretty much whatever is remaining if we remove that set from the picture. So if I was to remove this set, well, I'm going to remove all this blue bit. And I'm also going to be removing the boundary, right? The kind of black boundary. So I'm going to put a dashed line for that black boundary. And now, so you can see what remains is open, because it's only just dashed lines everywhere. So a set is closed if the complement is open. And it's a very, very logical definition. You know, we're just very lazy people. So we just said a set is closed if the complement is open. Very simple stuff. We've talked about the two-dimensional space. Let's look at the three-dimensional space. And the definition is very, very similar. So it's closed. So let's look at the open case first. So if I have a three-dimensional cube, let's say, that looks like this. And it's open, let's say. Now, it's a very, very simple definition. So all we do is change the circle to a sphere, like this. So no matter what point I pick in this kind of cube, I'll always be able to draw a sphere around it, such that that sphere is always within this cube right here. And the closer I get to the boundary, the smaller the radius of that sphere is. Okay, so perfect. And again, a closed cube that looks something like this is closed because the complement of this cube is going to be open, you know. So if I was to get this cube out of the picture, whatever is going to be remaining is going to be open naturally. So that is what a closed set is. Amazing. So that is the definition for R3. And the higher dimensional spaces work in a very, very similar way. So R4, R5, R6, so on and so forth will work in very, very similar ways. And there we go, guys. I hope you guys enjoyed the video, and I hope you guys understand what open and closed sets are now. Thank you very much for watching this video, guys, and I'll see you guys in the next video.